All right, hello everyone. Welcome to today's CSE365 class. We are on the assembly crash course module. It is due as this nice website. Let's refresh to make sure it's accurate. Yeah, 6 days, 11 hours, and 55 minutes till this assignment is due. I believe the syllabus says that the next assignment just opens up immediately after. I'll confirm that. Whatever the syllabus says, that's what's the truth. So we've got about a week left on this assignment. I highly encourage everyone to start as soon as you can. I mean, I feel like probably every professor in all of your classes tells you this, and then inevitably half of you wait until the very end, but the server load spikes like 10x at the very end. Your life will be more frustrating. Pretend the deadline is the day before, and any server issues just won't exist anymore. We're trying to resolve the server issues, but only so much can be done when server load spikes 10x on the last few hours of the assignment. So there's your warning. Okay, so does anyone have any questions actually about this class as a whole? Is this like class making sense? I know it's like kind of different than some styles of class where it's just like 100% assignment. No one has any questions about like the structure of this class? Oh, we got a question, yeah.
So is the first like module for 39, 30, is it like by level or is it just by each module?
It's by each module, yeah. So each challenge is equally weighted within a module, and then each module is equally weighted. Yep. Cool. All right, well then let's jump into it. So we were previously demonstrating on Tuesday this building of stir length, and before stir length we did stir copy. So we showed the assembly for how we could build such a thing. So I guess here's like a little refresher to make sure everyone's on the same page from Tuesday. The way that we implement stir length is as follows. We have these strings here. So I guess in this case we were demoing this as an edge case at the end. But we have two strings somewhere in memory. So we have this hello label, very similar to the underscore start label or a stir length loop label or a stir length done label. What the label is it's just a reference to memory. The exact location is not known yet. But for example, when we make this program, we know, for example, that underscore start, which is the entry point to it all, is at this address, 401000. Suddenly, there is an address associated with this label, and now all of these things that reference labels, it actually happens before we load it into memory. It's actually when we build this ELF file that all of these addresses get figured out and meaning is assigned to it. So for example, we have the potential to jump if equal based on this previous thing to stir length done. Where the heck is stir length done? Well, when we built this file, so we assembled it and then we linked it, if we use something like objdump, which is a tool for disassembling a binary, and we look at it, it says stir length loop has this value. So really these labels are just integer values associated with a location in memory. So when we say jump if equal to stir length done, really the actual assembly that gets produced is just making sure it's going to that address that got decided when we built the program. So the assembler, the linker, they decide locations where everything's going to go, and it patches up the code and makes sure that we're going there. Sweet. Okay, so that is how that works, if there was any confusion about that. So the way that we implemented this is we have this thing called hello. And actually, does this work if I make this, can I say x/s hello? Yeah. So the hello label got this address right here when we produce this binary, 401021. So if we ever reference that thing, we're referencing the location where all of this data is in memory. So this is at, this capital T is at 21, this H is at 22, it's et cetera, et cetera. It's linear memory. So for example, I could show 8 bytes of hello. And you'll see that there's just individual bytes. It's linear memory all sequentially loaded up into memory. And if we look far enough, eventually we get to a null byte. So I guess we didn't print quite enough. Where the heck is this null byte? Right here. So at hello plus like 42 or something, looks like 42, there is a null byte. And that is how we've decided to give meaning to the end of this string. So everyone here has used C, right? Everyone's written programs in C. You're familiar with the fact that a C string is null terminated. That's just a decision. You don't need to have your string be null terminated, but it is a convenient way to terminate a string. Alternatively, you could just pass around a size of some data and that data, and now you also know the size and when it terminates. There's just different styles to how you want to do it. This is kind of nice because it means we don't need to pass around a size. Unfortunately, it means we need to find the null byte eventually. And so there's kind of trade-offs there. But in this case, we are doing null terminated strings. And we are doing that in assembly specifically with this dot string thing, which means literally when we build this binary, this elf, put these raw bytes into memory plus a little null byte at the end. So instead of dot string, if I wanted to, I could do like dot ASCII, which means all of these values are ASCII values, and put the null terminator myself. It's just kind of like a convenience thing, dot string. Okay, so the way that we're doing this stir length is we start by initializing RAX to 0. And when we built this algorithm, the idea was that RAX is going to be the length of the string. Before we've done any work, our initial situation is that the length is 0. Then we put into RBX the offset to hello. So this is the location of hello. This little like offset thing, this is an assembler syntactic thing. This is not actually an x86 concept, this offset thing. It's just because we're working with labels. So there's like a question here. Do I mean 8 bytes at what's located at hello, which is what this would mean? So this would mean pull 8 bytes out of hello and put that into RBX. Or do we mean the location of hello? And in this case, we mean the location, and the way we specify that is with offset. Then we begin our looping mechanism. So the way we implement this is at a high level, we're just going to keep walking until we find a null byte, right? If we think about, we've determined that a string is something that ends with a null byte, what are we going to do? Keep pulling a byte out of memory sequentially until we find a null byte. So the way that we do that is we pull out of RBX. So initially RBX is the very first byte of our string, and we move a single byte. The reason we're moving a single byte is because, first of all, we only want to look at a single byte. But there's kind of like this implicit byte pointer thing here. We don't need that because we're moving into CL, which only takes 1 byte. So it's implicit that, hey, we're moving 1 byte out of memory. If we had instead done RCX, we would implicitly be pulling 8 bytes out of memory, or explicitly a keyword pointer. But we want to look 1 byte at a time. So we pull out of memory 1 byte and we check, is that thing a null byte? Is it 0? Oh, there's a question.
So what are the square brackets?
Yeah, good question. So this square bracket notation, generally speaking, means go to that location in memory. So treat this value RBX like it's an address, like it's a pointer. And specifically, this square bracket notation means now dereference it. So it's kind of like the equivalent of if we did like star RBX is like kind of more or less the equivalent idea of bracket RBX. So it means, because RBX doesn't have to mean, like there's no meaning of RBX. Just because we decided to say put the offset of hello in there, we could still like, I don't know why you would do this, but you could just treat this as a normal integer and just start like adding 1 to it, like do whatever the heck you want with it. Or we could pretend that these are like ASCII values currently sitting in here. It's up to us. We decide at this moment, we're treating it as an address and pulling out of memory. So for example, if we had done this instead, this would be an assembly error because we'd be trying to move just this 8-byte value into a 1-byte register, and you can't do that. We could do this instead. But specifically, this notation means pull out of memory now. Square brackets pull out of memory. Okay, so we pull out of memory 1 byte, and we check, is that thing a null byte? Well, if it is, so jump if equal, so if it is in fact equal to a null byte, we are done, right? Because as we said, this C string ends with a null byte. So let's get the heck out of this loop thing because we determined that we are currently looking at a null byte. Now to make this iteratively function, right, to like keep making forward progress, the next thing we do is we add 1 to RAX. So RAX is our string length currently as we're computing it. And so we add 1 to it because we determined that what we just looked at is not a null byte. So this thing is now, 1 greater than we previously thought it was. And then we add 1 to RBX, which means, if we think back to our loop, get ready to look at the next byte of memory and then do it all again. So these two things kind of allow us to make forward progress, keep pulling the next thing out of memory. This thing actually pulls the next thing out of memory. And then we kind of also at the end of class demoed this int3, which creates a breakpoint for us, but we don't technically need that for this algorithm. And this is str length. This isn't necessarily a very optimized version of str length. We could go and look at, who wants to see what str length actually looks like in libc? Does anyone care? All right, we got some hands. We'll just quickly look at it. So the way that we're going to look at it in libc is just another elf file. It happens to be located at this path right here. We could obj dump this thing as well. And now we're looking at the assembly associated with libc. If we go to str length, well, let's see here. Got a whole bunch of stuff going on here. So we're looking at where is our C move? Str length. There might be layers of indirection here because I'm not seeing like a looping concept. I'm seeing compare, C move. We're not going to look at the actual implementation of str length. It's just going to make things more confusing than it needs to be. I'm not even sure. I think we're probably even going to have some indirection and we're going to go to a different implementation of str length depending on specific things. Ignore that. We'll get there on the Discord if someone is really interested in it. Okay, so this is our implementation of str length. So we're able to measure this string right here at hello. We could, for example, say hello2 and then switch this from hello to hello2. And now, well, I guess we didn't show the previous result, but this would now allow us to measure this length in assembly. So let's do that. If we break at str length done, whatever the heck is in RAX at the end is our length. So if we continue, we see that there is hex 16 in here. So is the length of this string hex 16? Let's see. If it's not, then we have a bug in our implementation. Oops, we don't need that. We want another terminal. That looks pretty good. Hex 16. So our algorithm at least works there. There might be some weird edge cases we're not thinking about. So for example, if we wanted to really test this, what happens if it's an empty string? What do we do? It should be 0. Sure enough, we look at REX, it's 0. We could do kind of maybe if we think in the C world, what should happen if we push a null pointer here? So let's say, sometimes you pass around null pointers. Does our implementation support a null pointer? The answer is no. We are dereferencing this thing, which means we'd be dereferencing a null pointer and we'd crash, but we can see that to show that it doesn't work. And then we try to pull out of memory at RBX, but RBX is currently 0, and we get a segmentation fault. So we don't support a null pointer. You could decide if we wanted to support a null pointer. For example, we could compare RBX with 0 and jump if equal to stir length done, right? Right at the very start, just compare it. Is it a null pointer? Get the heck out of there if it's a null pointer. If you wanted to be able to support a null pointer, but maybe we don't care about supporting that. Okay, now this is there's kind of a little bit of a mess here, which is, there's a question in the back, yeah.
I'm not sure how we are moving forward to this.
Yeah, so let's actually watch this unfold. So we'll just do ABC as our string that we're looking at. So hello to ABC, and let's watch that unfold. Maybe that'll answer your question. So it's very useful if things are like, especially when there's a bug in your code, to just start stepping through the code and like looking at registers, looking at memory, and making sure everything is what you're expecting. So we initialize REX to 0, and we initialize RBX to what the heck we're about to do the length of. If we look at this in GDB, this RBX value, we can see that RBX does in fact contain our string ABC. So we've at least set things up correctly with our initialization. Now, the next thing we do is we pull out of memory at RBX and put that into CL. So we're pulling 1 byte out. What are we expecting to come out of memory? What's going to end up in CL when we step to this instruction? Does anyone know what is going to be in CL when we step? The letter A, and specifically it's represented with ASCII. So if I step, we just step through this instruction. In CL, aka RCX, we have this value 61, hex 61. If we switch back over to the Python world, we can see what the heck hex 61 is represented as an ASCII character, and that is the letter A. So hex 61 is A. Okay, we check, is that 0? 61 is not 0, so it's not equal. And we're about to do a jump if equal, which means we're not going to take this jump because guess what? It is not equal to 0. So we step, and we're expecting to now be on this add REX1, right? We're not expecting to break out of this loop. So we step, and guess what? We are on this add REX1. So RAX is currently 0. We're about to increase it by 1, which means we're expecting RAX to be 1, which is great because we've processed 1 character. The string is at least 1 byte long. So we do that. And then we increment RBX by 1. What the heck is RBX? Maybe we forgot. RBX is the string that we're measuring the length of. So when I step and add 1 to this is now what RBX is. You can see how GDB is treating it as a string. It's because I'm telling it, like, hey, print this to me as a C string. So it's kind of confusing a little bit, like, how the heck does GDB know? Well, GDB has some sort of stir length implementation in itself so that it can print to me. But we can see we're no longer pointing to the string ABC. Now we're pointing to the string BC, which is just 1 into the string ABC. So we added 1. If we keep doing that, and then we jump back to the beginning of this looping mechanism. Specifically, we do not jump back to our initialization logic. That would be no good because then we'd push ourselves back to 0 and push ourselves back to the beginning of the string. We don't want to jump back to our initialization logic. We want to go back to our stir length logic. So we step. We're going to pull 1 byte out. What are we expecting to see come out into CL? What's going to be in CL? A B, yeah, exactly. So the next thing, and we look at this is hex 62. Turns out A is 61, B is 62, but we can confirm that with something like Python. It's the letter B. We are feeling probably pretty good. Maybe we're just missing the edge case surrounding breaking out of this loop, but so far everything's working as we expect. We step, it's not equal to 0, so we're not going to take this branch. We add 1, so currently the length is 2, and we go back to the start. We pull the letter C out, so we see that RCX is 62. I'm going to tell you, maybe you're seeing the pattern with ASCII. C is going to be 1 greater than B, so it's going to be hex 63 is going to come out of there. So we see hex 63 comes out. Is that 0? Still not 0. Go through, add 1, go back to the start, and now something more interesting is going to happen. We're going to hit finally a different case of this. We're going to pull out of memory, and what is currently in memory at RBX? It is an empty string. Before the beginning, it was ABC, empty string kind of, then BC, empty string, then C, empty string, and now we're just at empty string, aka null byte in memory there. And now when we pull out of memory, it's not going to be 61 or 62 or 63. What's going to come out of memory is a null byte. So we step, a null byte just came out of memory. We compare CL with 0. Guess what? CL is in fact equal to 0. So now we're expecting this jump if equals to not just fall through. We're going to go to stir length done. So when I step, we're expecting to go to stir length done. And I step, and sure enough, we're at stir length done. And our results, which we're saving in this RAX register, is 3. So one of the big ideas in computer science is abstraction, and kind of a corollary to that to some extent is like not repeating yourself. So if we wanted to get the length of, let's see here, if I wanted to get the length of hello and hello2, and maybe by saying get the length of, like, we're not printing to the screen yet, though we'll be printing to the screen on Tuesday. We want, let's just say, to momentarily put into RAX the length of hello, and then momentarily put into RAX the length of hello2. So we could do that. We could do the following. We could copy all of this. We could paste it. We could rename some of our labels. So stir length loop 2. Make sure we go to stir length done 2, stir length loop 2, stir length done 2, and copy our initialization logic right here. Oh, I did already copy it. And we could do hello here. We could do hello2 here. And now at stir length done, we'll have the length of the first string, and at stir length done 2, we'll have the length of the second string. Just sanity check that that does actually work. So let's make this. Let's break at stir length done and break at stir length done 2. We continue 2A as a reminder, in case anyone doesn't think 2A is a convincing answer. If we take the hex of the length of this string, it is 2A, so Python agrees with us. And if we continue again, now we have 3, and ABC is length 3. So great, now we can do this stir length operation twice. And hopefully it's clear that if you want to get the length of, let's say, 100 strings, like, what's happening here? Why we're not just going to keep copying code? That's no good. So what we do, or what we can do, is do something called a function call, right? We've all done function calls, whether it's in C or Java or Python, or really, I'm sure any language you've used has some sort of call mechanism. And all call really is I need to abstract this, and I don't want to just literally duplicate code. I want to be able to use this functionality of this program multiple times. x86-64 has a call instruction. So this is supported directly in the architecture of your CPU with the call instruction. And we will demonstrate how it works. So if we want to implement some sort of function here, so let's actually go ahead. Let's go ahead and implement that. So let's get rid of our duplication. Here's what we can do. We can, well, we have a couple of options. Let's start with like something slightly better where we don't actually need to use call yet. Is that true? Yeah, let's use something where we're not actually using the call yet and show that it works, and then we'll use the call instruction. So if I want to, actually, is this? No, I think it's going to be easier just to go straight to call. So let's go ahead and call this thing right here. So we have stir length, which has, and then we also have stir length loop, and then we also have stir length done. So all of this as one cool thing. If we want to execute all of this code and then come back somewhere else. So for example, let's say I want to get ready to do the stir length logic for RBX, and then do the stir length logic for RBX again. And we want to like sequentially do that. And in fact, hopefully it's clear, RAX being 0 is the initialization of stir length, right? We start out at 0. And then maybe somehow we want to say something like return RAX, right? This is kind of what we're building up here. And then there's kind of also, we're saying, give me what you want the length of in RBX, right? This is what I'm trying to build up to. So someone puts the string that they want the length of into RBX, and then we like return RAX to them or something. We like want something that looks like this. And then what we could do is like call stir length here, and then like call stir length here, right? We're slowly getting there. Okay, if we want to do that, well, there's a few things. So the first thing is, as I said, there is a call instruction. So this is actually how you do it. We call stir length. And call stir length is a jump instruction plus a little bit more. We're going to unpack what that little bit more is. And then somehow as part of this jump instruction, there's like, we need this mechanism of, when you're done with that, now come back. Like we want this to be the next executing instruction after stir length has finished doing all of its stuff. And then we want to do that again for this, right? So we do hello, we do hello too, and hopefully at least here, our result is in RAX. Our result is in RAX, right? This is what we're trying to do. So we have this thing that we want here, which says, give me what you want the length of in RBX. Well, we already did that, right? When we set this up, we move the offset of hello into RBX, and I'm telling you call stir length is like jump stir length. So it's already in RBX. We've taken care of that. That's done. The person doing the calling has set that up. The caller has set up the fact that this address is in RBX. Now what we want to do is somehow return RAX. This is kind of like not actually what we want to do. All we really want to do is just return, like get the heck out of here. The result is already in RAX. There's no real concept of return RAX. The value is already in RAX. Really what we want is like jump back to who called me, right? Because as I said, this call thing here is jump to stir length. Now we just want to like jump back to, in the first case, to right here. Oops. In the first case, to right here. And in the second case, to right here, right? And we can put a NOP instruction so that all makes sense, right? We want to come back to here. We'll even put a NOP instruction here. We want to come back to here, and then we want to come back to here. So how the heck do we jump back to who called me? Well, we could almost imagine for this call mechanism, right? If instead of call, we did jump, we're like, all we're missing is how the heck do I return? One way that we could do this, so one of our registers we're not using is RDX, right? So we said that there's RAX, RBX, RCX, RDX. We could almost like move into RDI this like return here 1, right? We like move into RDI, return here 1, offset, return here 1. And then we could move into RDI, return here 2, not RDI, sorry, RDX. and move into RDX, offset, return here too. And now we like jump to stir length, and then all we need to do here is jump to RDX, right? And we've just kind of implemented it. We save some location into a register, into RDX, and then we jump to stir length, and then at the very end, we do a jump RDX, which brings us back. So we're putting in what we want the length of, and when you're done, where to come back to. Let's see this in action. We're missing a colon there. If we make this, oh, well, I guess semicolon is not the commenting thing here. Is it // Let's see. Well, I guess we don't really care about the comment. Let's just do that. Oh, and I killed the terminal. PS1 equals cd live assembly make. Okay. So we put this address into RBX. This is what we want the length of. We put where we want to come back to into RDX. So is this correct? Well, if we do x/4i, so x/4i means look at this location in memory and print it to me as 4 instructions. It is. So we've kind of set ourselves up. Now, as long as we can jump there, we're good to go. So let's break on stir length and break on stir length done. And let's continue. So we're at stir length, and so we're setting up RAX with 0. We see RDX already has our correct value in it. And now what we need is stir length done to have the correct value in RAX. So if we continue now to stir length done, 2A is here. We haven't messed with RDX, so RDX is still pointing at here. So x/4i RDX, that's good to go. And so if we step, and then we step, we returned, right? So we kind of like called into something. And I know I previously told you there's a call instruction. We're getting there. We're like building up to the call instruction. We saved our location that we need to return to, and then we jump back. And now we can do it for this string. So we got 2A. This is good to go. We got our result. We step. We say, hey, what the heck am I measuring the length of? We're putting that in RBX. And once I'm done processing the length of that, where should I come back to? We're putting that into RDX. And then we process. So we've got RDX is pointing to this. Oops. Is pointing to this. Whoops, we don't care about that. That's where we're returning to. 4i of that location that has return here 2 at it, right? Just this NOP. So this very first thing, it's the NOP return here 2. That's in RDX. RAX is currently 2A. Nothing set it to 0 yet, but don't worry, we're about to set RAX to 0. And RBX contains our string, right? We set everything up correctly. It's got ABC. So if we continue, or I guess first let's step. This is why we initialized RAX to 0. Our move RAX 0 thing, just 0.RAX. So we're ready to start processing again. We continue. Now we've got 3 in RAX, and we step, and we step. And guess what? We're back now at return here too. We implemented this ability to go do some work. Oops. Go do some work and then come back, right? So we load up what we need to load up. We jump there. We load up what we need to load up. We jump there. This is such a common thing. And there's one thing we're not considering. So there's 2 reasons that the call instruction exists. One reason is this is just such a common thing. You're like going to constantly be calling out to other functionality. So setting up RDX in this way is like, you could imagine maybe some like jumbo instruction called call. And maybe what call does is it moves the next address into RDX, right? You could see how like that could be how it was defined, that we move the next address into RDX. Automatically, we just look past the call instruction. We say it was right here, put that into RDX, and then we also do a jump. Like you could imagine this jumbo instruction that performs both of those tasks in one. That's kind of how call works, but not exactly. Oh, and then also, well, yeah, I guess you could jump to RDX here, but you could almost imagine instead a ret instruction where ret is just jump to RDX, and you could build up this architecture that does this, and that would be a perfectly valid architecture, except for one tiny but really important issue. We've only got so many registers. Now, you could dedicate RDX to this task of doing this, and you basically tell anyone else, hey, stop using RDX. But what happens if you think about in recursion? So maybe you're haunted by the term recursion from previous computer science classes. But we can have this concept where we want to be able to call stir length in stir length. Obviously, stir length isn't implemented that way, though we could recursively implement stir length by, instead of jumping to stir length loop, we could call stir length back and add one to the RAX after that. So that was you could imagine a recursive construction of stir length. But if we had this setup where we were recursively calling a function, we're going to clobber RDX here. RDX is going to get clobbered. And so we said that we're going to save where we're going to go to into RDX. Well, as soon as you do a call within a call, RDX is gone. So actually, we don't even need to worry about the recursion case. Just imagine a function that calls another function. If RDX is like our trail back can only be size 1 because RDX can only hold one return back to location. This does not work. We need to be able to support some sort of infinite call stack, ideally, or at least a really long call stack. And we're not going to just start taking over every register as part of our call stack. Maybe, okay, RDX is used, let's use R8, and then let's use R9, and let's just save this breadcrumb trail of who we called into all these registers. It doesn't work. We got a finite number of registers. This is, in fact, not how it works. So this is, though, going to work. So if I get rid of this and do call stir length, call stir length, and I do have this ret. This is, in fact, how you do this in x86-64. The question is, how do we get away with this without saving where we're going to return to into a register? How does this actually function? This is how it functions. We use the stack. We use memory. We start saving into memory where we're going to return back to. So rather than using registers as our trail back through this call hierarchy, we use memory. Because guess what? Memory is, it's not infinite, but compared to registers, it's practically infinite. So let's go ahead and make this. And we're going to see it compile, or it assembled. It's totally good. This call instruction really does exist, and this ret instruction really does exist. And I'm even going to argue to you that this is the correct setup for all of this. But how does it do it without saving it to RDX? What the heck are we saving where we need to jump back to? So if I step, and we've set up RBX with the location we're about to grab the length of, so x/s RBX. This is some longer string, and it ends now. If I step, assuming I'm not lying to you, the next place we're going to be is inside of stir length. There's a jump to stir length. It is a jump to stir length, except we saved the next instruction onto the stack. Automatically, there's this thing called RSP that I've been ignoring, and RSP is pointing somewhere in memory. It's a location in memory. It's not going to cause a segmentation fault, assuming your RSP is set up correctly. Technically, you can move anything into RSP and then get a segmentation fault, but at least when your program starts, RSP is in a valid location of memory. And actually, before we do this, I'm going to show where it was before because we were kind of ignoring it. Or maybe you saw it and were ignoring it with me. RSP is currently pointing to this address, right? E2F0, E2F0, it's right here. This is the current location. When I do this call, RSP goes up by 8. So actually, That's not true. It does not increase by 8. It actually decreases by 8. So this, we went from F0 to E8. RSP is now pointed at E8, which is 8 less than it was previously. And this right here is now sitting in memory. And if we look at this thing is my return here 1. This is where we're going to return to. This call automatically put it in memory based on RSP. It just did it for us. Very convenient. It's like this super instruction that did a jump and modified memory. Now, if we'll break at stir length and break at stir length done, and we'll continue to stir length done, because now the thing you're wondering, right, is like, all right, we need to see this ret instruction in action. The ret instruction is going to look at RSP. It is going to do the following. I guess we'll type it out for you so that you can agree that this is what's happening. We are going to move into RIP RSP. So we're going to take whatever the heck is at RSP, right, which is this value. We're going to move that into RIP, or you could say like jump to this thing, whichever makes more sense in your head. Unfortunately, both of these things are not valid x86-64, but there's no reason you couldn't design an architecture that had the ability to do this. And then we're also going to do add RSP 8, because there's also this important thing of we've got this was previously in 2F0. We add 8 back to it. We'll have RSP back where it initially was. We're good to go. So we move into at RSP. We move that into RIP. And at the same time, right, obviously, I mean, maybe if you're worried about the ordering of this, you could say it happens simultaneously, but maybe instead we'll say add RSP 8 and move into RSP, or move into RIP RSP minus 8, right? Then you could do these sequentially rather than all at the same time. That is what a ret instruction is. So let's see that in action. So if I step instruction, we're going to see that we're back to the return location at 40100C, and RSP is restored back to 2F0. And RSP back to E2F0, and RIP is right here. So that is call in ret. We, instead of using a register to say where the heck we're going back to, we use memory, and specifically memory at this thing called RSP. And I guess we could watch this happen again, right? We could continue, and suddenly we have this location now sitting in memory, and we continue, and we're about to do this unwinding thing with this ret instruction, and now we're back to return here too, right? With the second result being in RAX. Does anyone have any questions about call and ret? Yeah, there's a question.
So do you need to have the return?
No, that's a good point. Yeah, we don't need this anymore because nothing, that's just for the assembler's capabilities. The way that it works when we do call stir length is it automatically is putting into memory whatever this next instructions location is. Yeah, good point. We do not need that label. Does anyone else have any questions about how this is working? Yeah, there's a question in the back. Yep.
So x86 only uses that for keeping track of the addresses.
I'm not, it's been so long since I've worked with MIPS, I don't remember the calling convention there, like how it does calling. Maybe MIPS supports like a depth 1 call using a register. Like you could handle depth 1 calls with a register, or even like depth 2 or depth 3 calls if you're willing to sacrifice 2 or 3 registers. The issue is you just can't infinitely call. Does everyone know what I mean by like a call depth? I guess to further make sure it's very clear, test.c. What I mean by call depth is like if we have int stir length, and what we do here is like call stir length, right? Main calls stir length, and then maybe for some reason we also have foo, and stir length calls foo, right? This would be like someone called main, or maybe you say no one called main. Someone did actually call main. So then we go increase the depth by 1 because now we're in stir length. But then stir length calls foo, and somehow when you do all of these returns, like if we return here and then return here and then return, I mean, I guess we're back here, but we could say return here. Somehow we need to like unwind this hierarchy of calls. Like someone called stir length, they called foo. Foo needs to get back to here. Who needs to get back to here? And you could like scale this out times 20, times 30, times 50. You could have an arbitrarily long call depth. Or you could have recursion where foo calls foo. And then like, I mean, if you do this, this is going to run forever. But you know, you've seen recursive algorithms, you know how to make them break out. That is why we need to put it in memory. Because memory, I mean, we got a lot of locations in memory. Just in one page of memory, so one page of memory is 4096 bytes or hex 1000 bytes. We divide that by 8. We could have a call depth in just one page of memory. In 1 kilobyte of memory, we could store, or I guess 4 kilobytes of memory, we could store 512 depth of calling. Okay, so this is such a common thing of this need to like have this recursive data structure, right? It's kind of this recursive data structure. If we called something, this would go up higher and higher and higher. So I guess we could demonstrate that real quick. If we have, let's say, we will get rid of all of this. Maybe we'll want it back later. We'll throw it over here in our scratch pad in case we decide we want that back. If we define start and we define foo and we define bar and we define baz, right? And we call foo, call foo, and we'll just say then nop. And foo just does call bar, and bar just does call baz, and then we do ret, and then of course we want to return back up. Like we just have this calling hierarchy, right? So start's not really a function, but you know, whatever. This is where we're starting. It calls into here, calls into here, calls into here, and then we ret, walk our way back up. If we do this, we will see that the stack, this piece of memory goes here, and then this is going to call bar, which is going to go here. So now you can see we have 2 code locations in memory. That calls this, so we've got this in memory, and you could have an infinite depth to this, or not technically infinite depth, but very large depth to this. And then if we step, we return. You'll also notice that here, now that RSP is pointing here, it didn't like wipe out memory. That location is still in memory. It's just not immediately relevant to the next person calling ret, because the next person calling ret just looks at wherever the heck RSP is. And then we step, and then we step, and suddenly RSP is back to the start, right? And we've got these 3 locations still living in memory, but yeah, they're not utilized. Yeah, there's a question.
What if we are at depth 2 and we want to save some value on the stack?
Yeah, that's a really good question. So previously we were doing this thing where we were, let's see here, using RBX to determine like my argument or my parameter to my function. That's how we were supporting this. We were using RBX to put that in. Well, what if you're calling something that takes an argument, and then you're calling something that takes an argument, and then you're calling something that takes an argument? I mean, you could load it up into RBX and then RCX and then RDX and do that, but similar to this return problem within a function, eventually you run out of registers. This isn't going to work forever. Because what if when you return, there's still more work to do on that argument that was passed in? You might need to keep this around forever. There is a solution to that. In the same way that call kind of like pushes onto this stack data structure. So let's, for example, say that foo takes 1 argument, and we're going to keep using RBX because we were using RBX before. Let's say it takes an argument, and we want to put 42 in there. And then here, we want to push in 33. And then here, we want to use an argument of 17, right? And obviously, these are very minified functions, but you can imagine in the same way that stir length performs some work, each of these functions could also have like do more work, and they're dependent on RBX to do that more work. This is not going to work because we're clobbering the RBX register. So initially it's 42, but let's say we pass in 42 and we want to keep being able to use 42 later on in this do more work, but we had to put in 33 into RBX, and now I've like lost my 42 value that someone passed me. In the same way that we push the return instruction onto the stack, we put it on the stack, there's another way for putting arbitrary things onto this stack, and that is the push instruction. If I do push RBX, the value of RBX is now going to go onto the stack. And kind of similar to how there's a call and a ret, so like call like puts it onto the stack, ret takes it back off the stack, there is a pop RBX. So I can save RBX into memory by using this style. I push RBX so that it's saved into memory. It's somewhere in memory, and then I call bar, and then I pop into RBX. And assuming that everything doing operations is like not messing with RSP in some bad way, and that everyone's like, if they push something on, you're responsible for popping it off, or it's all in a well-structured way, we're going to be good to go with this push-pop business of saving something. So here I could also do push RBX, pop RBX, and that'll allow me to save that value. And I mean, we don't necessarily need to keep it here. I mean, it depends if you're expecting 42 to still be around after here or not, whether or not you want to save it. If we do this, this will all end up in memory. So let's see that in action, this push and this pop operation. So we set RBX to hex 2A, so it's 2A, and then we call foo. In calling foo, we push our return address onto the stack. It's on the stack now. And we put into, well, we can see actually we have an issue here. We're about to clobber RBX with hex 2.1. So we're about to not save our value because we're about to just clobber it before we even attempted to save it. So this actually is not going to work. We need to move RBX 33 here, right? Oops. So we had this instruction right here. This needs to happen right here. So we need to save RBX and then set up our arguments to our call by putting it in registers or whatever, and then do the call and then restore RBX. This is like the safety zone of RBX. In between the push and the pop of RBX, this is like RBX is good to go. We're going to be able to get it back later. So we want to do the same thing here. So we push RBX. Now we can mess with RBX all we want, and then we can restore RBX. Okay, let's run that. And actually, I'm going to use hexadecimal values just so that it's easier to see in GDB that it's 42, 33, and 17. Cool. So we don't have to do this like hexadecimal decimal conversion in our heads. All right, hex 42 ends up in RBX. We call. In calling, we save this onto the stack. We save this into memory. We step, and we pushed hex 42 onto the stack. So if we did a ret right now, we would crash, right? If the next thing we do is ret, we're screwed because ret goes off of wherever RSP is pushing to. So since we've like done this thing of messing with RSP, we better get RSP back to where it belongs before we leave this function. As long as we do that, we're good to go. But if we ret right now, we're going to crash because 42 does not have, it's not allocated to us. It's going to be a segmentation fault if we ret right now. But fortunately, we do not ret. We modify RBX now to 33, which is totally fine. We've lost our 42 in terms of it being in RBX, but it's sitting in memory. We're not afraid. We're going to get our value back. We call bar. Guess what? That pushes onto the stack a return value. So now we're going to be able to return back to this function. The person who called us, we're going to be able to return back to them. And that person's going to be able to return back to the person who called them and also restore their RBX value, right? This is all living in memory, ready to go for us. And then we step. We save our 33 into memory so that we can get ready to mess with it to do our next call. You can see now we got 4 very important things sitting in memory because people are depending on these values. Even though they're not technically in their registers right now, When they come back, they're expecting these things to be there. Of course, a malformed function could wipe through this memory and destroy all of it. But assuming everyone's like living together happily and no one maliciously attacks my memory, we're good to go. And then we call baz. And so what do? Well, we push the return location now onto the stack, and then we're going to unwind this whole process. We're going to ret. RSP is currently pointing at an instruction address. There's also crucially an address that's allocated to us. So we're going to return back to where we're expecting to go. And then we're going to pop RBX so that, maybe this function does computation on RBX and wants its original RBX back. We're going to pop. That's going to end up in RBX. Guess what? Now RBX contains our initial value that we liked. And then we step again because we're going to return back to our caller because we didn't actually do any work. We returned successfully. Now I want my RBX value back. I want my 42 back because maybe I'm going to do some work on it. Obviously, we all know this is just an example. We're not doing any work on it. We step. Now I want to return back to the person who called me, and we step. And now we're all the way back to the beginning, right after this very first call back to NOP. And we had this whole recursive process. This could get complicated in arbitrarily complex ways, right? We could do more work, and then we might call baz again and load it up with like 15. And then we're going to like make the memory grow and then go down and then go back up and then come back down. There's a question.
So when you're in bar or baz, how do you access the thread?
When you're in bar or baz, so let's say we're in baz and crucially someone is passing to baz this value in RBX. You're saying how do I use it, right? So it's really just let's say the computation that baz is a function that adds 1 and puts it into RAX. So what I could do is move RAX RBX. So we're passing it in RBX. Guess what? It's actually there. It's truly in RBX because we moved it into RBX. And then we move that, let's say, into RAX because RAX is, let's say, our return value. And we do add RAX1 because we're the add1 function. And now this person that called into baz got this sweet add1 functionality. And if it wanted to, let's say, compute the value of RBX plus 1, it now just did that. And the result of that, it put the argument to do this plus 1 functionality into RBX, and it gets the result in RAX. Does that make sense? It's just literally we're able to just use RBX because the first thing we did, or the most recent thing we did before we called it, is we put the value into RBX. So there's really no, your mental model in C, right? When you're doing C, you're thinking of all of these things as nice abstraction layers, that these are all isolated things and they're all living in their own world. And sure, they can all call into each other, but they're living in their nice own world. It's not the case in assembly. Even though we have this ability to do this call stuff, nothing's living in its own world. It's almost like everything's a global variable. Everything is accessible to everyone. In C land, that's just one of the benefits of C, is that you get to simplify your mental model. And when you're working in stir length world, you really only have to be thinking about stir length. You don't have to be thinking about who the heck called me and what did they do and all of that. And the reason for that, and where we're kind of building to, is this thing called a calling convention. So you've probably noticed that I keep putting the result of things into RAX. This is the standard calling convention in regards to results. Whenever you call someone, by convention, not by x86 architecture requirements, but by convention, we put the result of work into RAX. That's just what we decided to mean with RAX. If you call something, you want the result, guess what? Your result is going to be in RAX by convention. It's just simply by convention. The CPU does not enforce this in any way. Everyone just decided that if I'm going to write some code and you're going to write some code and I want to be able to call into your code and get the result, everyone just showed up one day and agreed that RAX is where we're putting results of function calls in. I've been saying RBX as the argument. Now, this is in fact not argument number one. And you could imagine, right, that we have multiple arguments. Maybe I want to put into RCX hex 19 and move into RDX like hex 33. And maybe this makes sense in your head that if the result is RAX, well, what are the parameters? Maybe the first parameter is RBX, the second parameter is RCX, the third parameter is RDX. That would be way too simple. Unfortunately, that is not the ordering of the arguments. The ordering of the arguments is RDI. It's another register. You've seen, I guess I've actually been displaying it to you without you knowing it. I've been displaying this RDI register and also this RSI register and also this RDX register. You might be thinking, why the heck did you choose to display RAX, then RBX, then RCX, then suddenly jump over to RDI, RSI, and then finally come back to RDX? Why are you displaying these registers in this weird way? The reason I decided to do that is this is the calling order. RDI is the first argument, RSI is the second argument, RDX is the third argument. Technically, the calling convention goes past 3 arguments. I believe you can have up to 6 arguments going in registers. You could imagine the weird function. You've probably never written a function like this, but you could imagine a function that takes in 20 arguments. At some point, we're going to run out of registers. We're still playing this game of what the heck do we do with registers when we run out of them? I believe it's after the 6th argument, and this doesn't really matter for your purposes. We're not going to have things with over 6 arguments. I believe it starts passing through the stack. So it just pushes it onto the stack, and the person looking for the 7th argument just knows to look on the stack and look in memory. You could also imagine a scheme that doesn't use registers at all for arguments. There's no reason you have to use registers for your arguments. You could instead put them all on the stack, right? You could imagine the very first argument is right here, the second one is here, the third one is here, and they're just all living next to each other in memory. Maybe, we're limiting to 8-byte values as our arguments. And in fact, this is how x86-32's calling convention works. x86-32 passes arguments on the stack. It pushes a bunch of values onto the stack and then does a call. And the person that's receiving that call, right, the callee, just knows to look in memory for all of these arguments. And that totally could work. In x86-64, they decided that the first 6 arguments do not go on the stack. They go in a series of 6 registers. In fact, if I look at, I think it's, you can see x86-64 calling convention. There's this thing called CDECL, which is like the standard for all of this. And it talks about, where the heck is it? There's a whole bunch of rules to it. Technically, we're also following this thing called the System 5 AMD 64 ABI. You've probably heard of an API. An ABI is an application binary interface. And right here we can see that the first 6 arguments go into RDI, followed by RSI, followed by RDX, followed by RCX, followed by R8, followed by R9. Excess arguments go on the stack. We're not going to talk about floating point stuff. Technically, floating point stuff goes in some registers too, and so on. So this is the calling convention. Again, the CPU is unaware of arguments to a function. It just doesn't care. It gives you some registers, it gives you some memory, it says have fun. It's people that decided that they want to build complex systems and work together and make something that everyone can kind of agree on and interoperate between all these things, that those people decided this is what we're all going to do. And this actually allows us, let me show this C program real quick. If I write foo and I say int first arg, and we'll just do return first arg plus 1. And then I call foo of hex 17. Okay, so what's going to happen here? GCC test.c o test c. Oops. If we look at this, it's not thrilled that there's no return, but these are just warnings. We don't care about warnings. Maybe you should care about warnings, but we're not caring about warnings right now. and we look at this program, oops, and we go down to main, well, we haven't seen the LEA instruction, but you'll notice that the very first thing it does before it calls is it puts something into RDI. So then we call into this function. And if we look at, oh, wait, hold on. I don't think we needed to load it. That makes more sense. Right here, this makes more sense. That was calling something else that was putting something into RDI as its first argument. I think it was actually calling into main is what we saw there. But in main, we call foo. And the way that we call foo with an argument of hex 17, not lying here, the first argument goes into RDI. In this case, it's a 32-bit value, so it uses EDI, which is, of course, as we know, a subset of RDI. But every single time you write a function and you compile it with GCC, something that's following this calling convention, it is going to put this into hex 7, or it's going to put this into RDI, the first argument. Just to really hammer home, int arg2 plus arg2. This naming convention is really bad, but we're going to roll with it anyways. GCC, objdump, main. The thing we do before we call foo is RDI. It does it backwards. Maybe you think this is the correct way. The second argument goes into RSI. We just happen to put the second argument in first and then put in the first argument. Then we call foo. We look over at foo's definition. Foo ultimately uses RDI and RSI. It decides to save them onto the stack into memory. We haven't talked about RBP yet, but don't worry about it. Saving it into memory. Then it takes them back out of memory. This is unoptimized code. Let's quickly optimize this code. O3, oops, GCC, objdump, foo. Well, it still does it, whatever. Takes RDI, RSI, puts them into memory, then takes them back out of memory, kind of wasted its time. But it is now in different registers. And then it adds them together. It does some cleanup, it rets. Ultimately, though, the result is in EAX. The result is in RAX. We'll have a later reverse engineering module where we're going to look at real C programs and make sense of them. So some of this stuff that maybe doesn't feel super smooth, don't worry, it's a later module. We'll be reading C code as assembly soon enough. But this is the calling convention. And the reason for that is now if I compiled this program and all I cared about is this foo function. This foo function is super nice. The use case for it is immeasurable, right? Everyone wants to be able to use this foo function. We can compile it and the compiler is going to generate it where it's expecting these arguments to come in RDI and RSI. And now we could build a completely separate program, and that completely separate program could know how to call into foo because it knows put the first argument in RDI and the second argument in RSI. And this is how libc works. Libc is just this already pre-built thing, and all these functions are expecting something in RDI, or if it's two arguments, something in RDI and RSI, and everything just works together. All right, any final questions before I wrap up class? Yeah, question.
Are there any register which you can use without worrying about functions, like temporary registers in websites?
You want to do what without worrying about calling conventions?
Like you can use them freely without
Yeah, so there's, if you're curious about more of how this works, as part of the calling convention, it's not just arguments and the return value go in these specific registers. There's also, as part of the calling convention, this requirement that if you care about this value in, let's say, RCX, if you care about what's in RCX and you call, there is a definition on whether or not the caller is responsible for that register or the callee. Some registers, the caller is responsible for persisting. Some registers, the callee is responsible for restoring back to its original value. So it's in the calling convention. We're not going to go super deep into that right now. But yeah, there is also this like who's responsible for saving the contents of what register. And that's baked into the calling convention as well. Cool. Any more questions? Otherwise, we're going to wrap up. Cool. All right. Thank you, everyone, for attending, and good luck.